Okay, so this is problem number 7 from one of your problem sets. We have a 145 gram baseball. So we'll highlight that. It's dropped 12.0 meters above the ground. And we want to know what is the speed. Again, just magnitude only. If air resistance could be ignored. So that's a pretty simple setup. You can use conservation of energy principles to figure that out. And with this value, we can say that, so for A, let's draw it out for a second. So we have our baseball. It is going to fall a height of 12 meters. This mass is really 0.145 kilograms. And we want to know what is the velocity right before it hits the ground. So we know, we can figure this out by using pi chi equals pef kef. And we can say, well, at the very beginning it has 0 kinetic, and at the very end it has 0 potential. So really what you're setting up is its initial potential energy should be equivalent to its final kinetic energy, which is really setting up mgh equals 1/2 mvf squared. Well, masses cancel. We can then say vf squared equals, let's get rid of this half by multiplying both sides by 2. So we have 2ghi, okay, is equal to vf squared. If we take the square root of that, that's going to be our answer. So vf is going to be equivalent to square root of 2 times 10 meters per second squared times our height, which is 12. So vf is 15.5 meters per second. Again, assuming that there is no air resistance or air drag. So now we want to figure out, well, what if it has air resistance? Because we know that it's hitting now with a speed of 8 meters per second, which is substantially different from the original value, right? If there's no air resistance, it's hitting with this, and with air resistance, it's hitting with 8 meters per second. We want to figure out what the average force of the air resistance is, so F air. That's what we're trying to figure out. So in order to do this, sort of think back to this model now. Instead of it being g, it's not equal to g anymore. We need to figure out what that acceleration is. Now you can use energy conservation to figure that out, or you can simply use A. So you have Vf squared equals Vi squared, use kinematics to figure out this value. So that leaves you with Vf squared minus Vi squared over 2 times the displacement is equal to A. When you plug in, so now you have 8.00 meters per second minus 0 over 2 times 12.0 meters is equal to A. Okay, and then if you square this, multiply that, you should get your acceleration is 2.67 meters per second squared. Now you can use that to solve for our F air. So we know that if we go back to F net equals MA, we can solve it this way and say, well, our F net is FG minus F air equals MA. So negative F air equals MA minus FG. So we solve for mass times acceleration, so 0.145 times 2.67, running out of real estate here, minus its weight, which we're going to say is 1.45 newtons. That's going to give us negative F air. So it's going to be multiply that, negative 1.0628 newtons equals negative F air. Negative, negative cancel, so we're going to get 1.0628 newtons for the air resistance for this falling object. And keep in mind, as it falls, so Fg is going down, right? And F air is going up, and when we look at those vectors, right, we're looking at them as, okay, so F air is pushing against it, pushing up. We have a positive value, 1.0628. Okay, now we want to figure out the work done by, we want to figure out C, and we want to figure out D. So what is the work done by the force of air resistance on the falling baseball? So this is the one we're working on now. So we can say that, so this is C. The work done by air is equivalent to the force of air times the displacement, or delta x, cosine theta. We say 1.06285 times our displacement, which is 12.0 meters, cosine 180. I use cosine 180 because the displacement of the object is down, the force of air is up. The difference in this, right, if we put our vectors together, up, down, opposite, that's a 180-degree difference. Cosine of 180 is -1. Right? We already know this. So this is just telling us -1. So when we do our multiplication, we get negative 12.75 for 2 joules, and that is our answer. Not sig fig, but that is our answer. If we look at D, it's similar. So instead of using the work done by the air, we're going to use the work done by the force of gravity. So we're going to say work done by gravity is equal to the force of gravity times the displacement cosine theta. Now in this case, with the cosine here, we have the movement of the object is still down, the baseball is falling, the force of gravity is in the same direction. So when we line them up, there is, to get from this head to this head, I don't have to, there's no angle difference. So this is cosine of 0, which is a +1. So the force of gravity is actually doing positive work to move the baseball down. So we have 1.45 newtons, using 10 as the acceleration due to gravity, times 12, cosine of 0, and this is 17.4 joules. And that is the answer, not sig figged, to D. What is the work done by the force of gravity?